looking forward to hear what's new and what are the perspectives, the possibilities. Thank you.
Thanks so much. How's everyone doing? Good. Okay. I appreciate it. It's good that we're mostly be doing these lectures in the morning. I know after lunch is often very hard because everyone's a little sleepy, but hopefully you've had some cafe, and we'll keep it lively. A couple of things. Well, first, of course, thanks to the organizers and to all of you for this opportunity. It's a huge pleasure to be here. I haven't been to GGI, I think, in 13 years, but it's really delightful to be back. We'll get to the title of my lectures in a minute. Before that, just a couple of preliminaries. So indeed, I'm a professor at University of California, Santa Barbara, also at the Kavli Institute for Theoretical Physics. The reason I'm at the Kavli Institute right now is I'm running something called the Particle Theory Initiative. The idea is that the field of particle theory as an endeavor is so broad now, right? And it makes contact with so many different fields of science that there's an opportunity to maybe try to strengthen connections between different parts of particle theory and also strengthen the interface with other fields. So we have the pleasure of doing that through many of the opportunities that the KITP presents. And of course, I'd be delighted to talk to you more about building bridges between different parts of our endeavor. So coming then to the, before I come to the title of my lecture, one other thing, which is just a brief apology. When I was a PhD student, I severed the nerves that go to the back of my right arm in a bike race. And it leads to sort of an interesting disability as a physicist, which is that I can't write above my head on a chalkboard. Okay, so especially I'm not exactly the tallest person to begin with, so this is quite a disadvantage. As you can see, it was a bit of a stretch for me to populate this line. So I'm mostly going to be living here and down, but if you have a hard time seeing what I've written, don't hesitate to let me know, and I'll do my best. It usually gets a little bit better as I get warmed up, but I'll just apologize ahead of time. If you see me standing on my toes, that's the reason. So on to the title of the lectures. I was asked, I think the organizers prompted me to talk about naturalness, which is something that I spent a lot of time thinking about, and I still is a topic that's very dear to my heart. But I also realized that even myself, I don't so much want to hear much about the state of naturalness these days, because there's a general sense that it's not very good, and there's a lot of confusion about what it even means. And I find, especially in talking to students, that it can just be a complicated endeavor to talk about these things. So instead, I actually wanted to take a much sort of more ambitious approach to the prompt that I was given. And as a result, I've come up with what's a very cryptic title. But the first thing I'll do is try to explain to you where the title comes from, and then that'll also give you a sense of where these lectures will go. But briefly, just to help orient what I really want to talk to you about over the next 5 lectures is new ideas about symmetry in quantum field theories, in relativistic quantum field theories, relevant to 3+1 dimensions, many of which have really only consolidated over the course of the last decade. Now, this isn't just a talk on formal quantum field theory. Of course, this is about the theory of fundamental interactions. So my goal is not just to tell you about these symmetries, but then to make clear to you how they are relevant to the particle physics that we care about. And also to give you a sense in which they give us maybe a new mission as particle theorists, and especially you as students, which is actually to frame a new way of thinking about these symmetry-based problems that confront us in field theories. So I'm not just here to teach you about something this week. I'm also here to sort of recruit you into a movement to frame this thing that I'll call the generalized Hooft paradigm. So just for fun, I should also say I typically like to be very interactive in lectures, so I'll often ask you a lot of questions, and I hope you'll be willing to return the favor. Just out of curiosity, does anyone have a guess as to what I'm referring to here, what my lecture's about? It could be a completely random guess, just for fun. If you had to think, what does the generalized Hooft paradigm, what would you say it means? If you Google it, you won't get anything, by the way. So does anyone have a favorite? It can be silly. Yeah. Not very good. Okay, so that will be part of it. So here, generalized does indeed somewhat refer to the idea of generalized global symmetries, which is something that's come into focus over the course of the last decade. Okay, that's probably a reasonably fair guess. No silly guesses. But well, let's go ahead then and get started. So actually, I want to get started in explaining the generalized Hooft paradigm, not with high energy physics, but with condensed matter physics. And I promise you this will only be a brief excursion, then we'll get back to high energy physics. But in condensed matter physics, for a very long time, when we were trying to sort of organize and come up with a systematic understanding of the phases of matter, there was a beautiful paradigm that was given to us by Landau and his collaborators. And the Landau, so this was called the Landau paradigm. Does anyone just out of curiosity know what the Landau paradigm is at a sentence level? Yeah.
Characterize phases of matter by their symmetry breaking apart.
Absolutely. So the Landau paradigm is the phases of matter. I would say the phases of matter are characterized by the symmetries they break. So what does that mean? Well, let's take, for example, a ferromagnet, okay? So, a ferromagnet at a very crude level, right? It's just a material with a bunch of spins. So there is some symmetry. So just for example, ferromagnetism. Right, so if I think about what's the global symmetry of the system, well, there's like a global spin orientation of the material, right? Which is just an SU2 symmetry. So that's some group G. And then, of course, if we magnetize a ferromagnet, right, we align all the spins in some direction. That breaks this down to a smaller symmetry, which is just the U1 that's generated by the spin operator in some specific direction. And this breaking, right, is given by the VEV of a local operator, which is just the magnetization, right? And we say that's the order parameter for magnetization in a ferromagnet. And as with the spontaneous breaking of any global symmetry, of course, there's Goldstone modes. So in this case, the Goldstone modes, there's two of them, right? And these are spin waves or magnons. And this is just a nice example of what we mean by the generalized, by the Landau paradigm. If I have a phase of matter, what do I really mean? I mean, there's some overall symmetry G that characterizes the broad symmetry possibilities of the system. There is some local operator that acquires a vacuum expectation value that breaks that parent symmetry down to some smaller symmetry H. And then, of course, there are typically Goldstone bosons associated with the global symmetry breaking pattern. Now, it's possible, given some G, right, that I can have order parameters that break the symmetry in different ways. So in principle, there is not one unique breaking of G to H. And this might be what I mean by having different phases of matter. I have one system which has some overall symmetry G, but there's different ways, either different directions of some local operator or different local operators, which can break me down to different H's, and those are characterized different phases. All right. So, very successful for ferromagnetism. It's very successful for characterizing superfluids. So in a superfluid, for example, so this is ferromagnetism, superfluids. In a superfluids, G is a U1 symmetry corresponding in some sense to global particle number. But in the vacuum of a superfluid, there's some well-defined phase associated with the order parameter, and that phase doesn't commute with number, and so G is broken to nothing. And there are Goldstone bosons, which are phonons in the superfluid. Another good example, sort of the canonical three examples of the Landau paradigm, is just thinking about crystals. So of course, if we think about a crystal, let's not worry about the full Galilean symmetry, but naively speaking, before I worry about where everything is localized in the crystal, schematically speaking, the symmetry is rotations times translations. And then when I actually think the local order parameter, this is sort of the density of things in the crystal, this now breaks it down to the point group and discrete translations, right? And again, there are Goldstone bosons. The counting is a little bit more subtle because it's breaking to a discrete symmetry, but again, the Goldstones are phonons. So, decades of incredible success of the Landau paradigm. I give you a phase of matter. If you think hard enough, you can think about some parent symmetry, some order parameter as a local operator, and some daughter symmetry, and this actually allows you to uniquely characterize the phase of matter. So, okay, all great successful paradigms in physics, end in failure. And so after many decades of success, condensed matter theorists started taking the Landau paradigm to the woodshed, in the sense that we started to discover lots of materials that could not be characterized in the Landau paradigm. Canonical examples were things like the fractional quantum Hall effect, or topological insulators, which are things that in the bulk are an insulator, but have some conducting states that live on the boundary and are characterized in a topologically non-trivial way. And these were phases of matter that simply didn't fit into the Landau paradigm. There was no symmetry breaking pattern that could be used to distinguish them. And so for a long time, people went around saying the Landau paradigm is dead. But then something very interesting happened, really over the course of the last 10 to 15 to 20 years, is people realized that actually the Landau paradigm was still a perfectly good paradigm. What was required was a broadening or generalization of our idea of what symmetry was. That we simply were insufficiently creative. The original Landau paradigm was based around really ordinary global symmetries, and then with some subtlety was generalized to gauge symmetries. But the recognition was actually that there's a much broader class of global symmetries that can be used to characterize field theories relevant to condensed matter physics, and that all of the phases of matter that violated the ordinary Landau paradigm could actually be completely characterized in terms of a generalized Landau paradigm where we had a broader notion of symmetries. And for the most part in condensed matter physics, those symmetries are things that are called generalized global symmetries. So they are higher form symmetries and non-invertible symmetries, and some of the things that happen when higher form symmetries have anomalies. And basically the state now is the Landau paradigm is alive and well, it's just we had to broaden our notion of symmetry. Okay. So that was my 5 minutes on condensed matter theory. But why am I telling you that now? Well, it's my belief, I think it's a widely shared belief, that we're in a similar situation in high energy theory. We're not in the situation, the story is not over yet. So unlike in the Landau paradigm where there was this idea that was very successful and then there were many exceptions and violations, and then the idea was resuscitated by a broadening of the notion of symmetry, as I'll hopefully explain today and in my next lecture, we have ideas about what symmetry controls in relativistic quantum field theories, the ones that we care about for high energy physics, which were very successful for a very long time, have fallen in disfavor because of a lot of apparent exceptions. And now there is at least a sense that by broadening our notion of symmetries, we may actually be able to bring the whole story back together. But the difference is this broadening is not yet done. So in some sense, the goal of my lectures will be to persuade you that we are in the middle of developing a new paradigm, this generalized Hooft paradigm. And I'll tell you about a lot of the pieces that I think fit together in it. But I also want to leave you with the charge that because the story is not over, all of you in this room get to help take part in finishing it. Okay. So what is the paradigm that's interesting in high energy physics and potentially under threat? It's the statement not so much that, so we're not interested in the phases of matter being characterized by the symmetries they break. But the one thing that I'm interested in high energy physics is what I'll call the Hooft paradigm. And the Hooft paradigm, we'll take as our definition, is that small parameters in QFT are characterized by the symmetries they break. Now, I'm calling this the Hooft paradigm because of a very influential set of statements that Hooft made in 1979. Up until this point, so outside this lecture hall, they're generally referred to as defining the notion of Hooft naturalness. We'll talk a little bit about naturalness in my lectures, but as I've already emphasized to you, I don't really want to get caught up in naturalness. People think that naturalness is a matter of philosophy, and we're not here to philosophize. We're here to do quantum field theory. So I'm really going to try to avoid using the word naturalness, and I really want to frame it in the language of a paradigm. So what did Hooft say? Hooft didn't actually say small parameters in QFT are characterized by the symmetries they break. But what he did say, and here I'm just going to quote this, at an energy scale mu, okay, a parameter, and here he emphasized, he uses the word physical. And so, of course, we should always keep that in mind. But even things that are not themselves physical observables can be related to them. There's some parameter, he called it alpha I. We know, of course, parameters are not constants, but they're typically functions of scale. This can be very small. Only if we made the replacement by setting it to 0, if that enhances the symmetry of the theory. Okay. So this is a very interesting idea. It's referred to often as Hooft naturalness. What does naturalness mean in this phrase? Well, people fight over what naturalness means, but to give you a loose characterization, at the time and even now, we ask ourselves a question. If you're given a quantum field theory that describes some aspect of nature, in particular, we think a lot about the standard model in particle physics. It has parameters of various sizes. And we really want to know, is the theory that we see, is it, we're only seeing a low energy effective theory, right? We don't know what the fate of the standard model is at arbitrarily short distances. And so what we want to know is, are the parameters that we see, are they generic predictions of some underlying theory in the UV, or are they special in some way? And the reason we care about that, right, is as theorists, we're engaged in a sort of strategy. We're trying to figure out how we want to spend our lives asking questions about nature. And if there's some parameter in the standard model that could be some generic output of some microscopic theory, it's interesting to think about where that parameter comes from, but it might come from some physics at the Planck scale that we'll never test experimentally. Whereas if we encounter some parameters that seem to be non-generic, right, they seem to be some special outputs of a microscopic theory, then we can think, well, okay, is there a way that I can actually explain that, explain why I see that? And then maybe come up with some predictions that I can then go use to guide experiment. And maybe I have some reason to understand that there's new phenomena associated with the special parameters closer to experimental accessible energies. So in some sense, asking this question is useful because it gives us a strategy. How should we spend our time, making predictions for physics that lies beyond the standard model? So loosely speaking, parameters that seem generic or seem to be understood from the microscopic theory as being generic outputs, those are natural. Ones that don't obey that would be unnatural. Maybe they can be made natural by broadening the theory. And so then we can go ahead and ask this question about the theories of nature, such as the standard model. Okay. And for a long time before Hooft, the idea was, parameters should all be order 1. Natural parameters should be order 1 in whatever the appropriate units are of the theory. And so what Hooft introduced with his idea of Hooft naturalness was that, well, it is possible to reconcile yourself with a small observed parameter if, when you take that parameter to 0, the theory has an enhanced symmetry. Okay. And the rationale for this really, for both pieces of this, right, the idea that all natural parameters of the theory should be order 1 in appropriate units, and the idea that they could be somehow smaller than that if a symmetry is restored when they go to 0, this is really just coming from the way that quantum mechanics works, right? Quantum mechanics, very heuristically, tells us that everything that is consistent with the laws of nature happens. What that means in the context of a quantum field theory, right, is in an interacting theory, all parameters are connected in some way by virtual effects. They all feed into each other. And so at the end of the day, that pulls them all towards whatever intrinsic scale the theory has. And what Hooft has refined this picture by saying is, well, that's true, but quantum mechanics respects the symmetries of the theory. And so, of course, one thing that transforms differently under symmetry cannot renormalize another thing. And so that allows us to understand maybe a way in which parameters could evolve separately is if they're separated from each other by symmetry. So that's the idea behind Hooft's idea of naturalness, which we'll call the Hooft paradigm. Okay, so this turned out to be a very powerful observation. It turns out to be incredibly powerful, especially when we think about QCD. And what QCD does is we go from very high energies to very low energies. I'll give you some examples towards the end of this lecture. But subsequently, the Hooft paradigm really started to fall apart. Maybe the most dramatic example of the Hooft paradigm falling apart is the discovery of an apparently elementary Higgs boson. And the reason why that seems to be an apparent violation of this Hooft paradigm is that we see a small mass parameter, which is dramatically lower than any other scales that might UV complete the standard model. And because that mass parameter, or the operator, the Higgs squared operator that it's proportional to, doesn't respect any symmetries. No symmetries are restored when we take it to 0. So it's very hard for us to understand why this parameter is small compared to any ultraviolet scales. All right. So that's maybe the biggest reason why people are giving up on the Hooft paradigm. But that's some sort of experimental fact. Even if we think about just theoretical facts, it's already clear that there are loopholes or exceptions to the Hooft paradigm. So really, even shortly after Hooft phrased this idea of Hooft naturalness, there were observations that it is possible actually to have parameters in a field theory which remain small as a function of scale without restoring a symmetry when we take them to 0. Just because there can be other effects that control how the parameters renormalize. And so this gave rise to a slightly expanded version of the Hooft paradigm, which was known as technical naturalness. And so technical naturalness is simply the statement that parameters are radiatively stable but this could be with or without a symmetry. Okay? So if you wanted to draw yourself a sort of space of these ideas, there's this idea of technical naturalness, and within it the idea of, sorry, they both start with T. This will be Hooft naturalness. So a parameter which a symmetry is restored when I take it to 0 will be radiatively stable, but it's also possible to come up with parameters that are radiatively stable without restoring a symmetry when they're taken to 0. Right, so these would apparently already be exceptions to the Hooft paradigm. We'd have small parameters where quantum effects don't make them large, but there's no symmetry attached to them. We'll talk about some examples of Hooft naturalness throughout the lectures, but I just want to give you one to chew on right now, which is you could ask, what about the masses of gauge bosons, right? So if I write down a gauge theory, even if it's just an abelian gauge theory, we sort of know that we don't write down a mass parameter for the gauge bosons. And normally what we invoke to explain why this mass is 0 is we say, well, look, gauge symmetry prevents it, right? So if I do a gauge transformation of the vector boson, clearly this mass term is incompatible with that gauge transformation. And similarly, if I spontaneously broke the gauge symmetry, or in the case of an abelian theory, if I did add a mass term by hand, it would be protected by a symmetry. And we would say it's protected by a gauge symmetry. Out of curiosity, how many of you in your lives as particle theorists have been told that gauge symmetry is not a symmetry, it's a redundancy? Right, okay, so actually we're told that this is an incredibly misleading statement, right? Indeed, gauge symmetry is not a symmetry. It's a redundancy of description. The reason it's a redundancy of description, right, is we insist on writing down local Lorentz invariant Lagrangian densities, and so we shoehorn the two physical polarizations of a massless vector boson into a Lorentz vector. And that gives rise to a redundancy, which is gauge symmetry. So from that perspective, right, gauge symmetry is not a symmetry at all, and we have no business claiming that this is protected with reference to a symmetry, right? Now we have other ways of justifying to ourselves why this is protected. One of them is just the discontinuity in the number of degrees of freedom between a massive and a massless theory, right? So a massless vector has 2 polarizations, a massive vector has 3, so the fact that 2 is not equal to 3 is another way that we can understand that this is a protected quantity. But that's absolutely not a symmetry in the way that Hooft meant. And so you might properly characterize the radiative protection of masses of vector bosons as an example of technical naturalness without Hooft naturalness. So already this idea, it seems powerful in some cases, but it falls at lots of hurdles. It falls at theoretical hurdles of examples where small parameters are not controlled by genuine symmetries. And it falls experimentally when we go out and we measure, for example, the mass of the Higgs boson, and we cannot understand why it is so much smaller than any other apparent scales that we might think of in the fundamental theory. All right. So it could be the case that the Hooft paradigm has simply failed, right? But the perspective that I want to take in these lectures is much like the perspective of the generalized Landau paradigm, that actually there's just a much broader notion of symmetry, and that if we can bring that broader notion of symmetry to bear on the Hooft paradigm, then we will recognize that it's actually vastly more successful than I think even Hooft believed when he originally formulated it more than 45 years ago. Okay. Yeah.
Okay, just to clarify, so essentially the difference between technical naturalness and the Hooft naturalness is this idea of generalizing these globals from this to gauge symmetry.
Oh no, I give this to you as an example. Yeah, so you might say in the same way that in the Landau paradigm, for example, a charged superfluid, actually the symmetry is a gauge symmetry, and so already even in the Landau paradigm, people were fitting in gauge symmetries. I'm giving this to you as an example because if we take Hooft, if you read Hooft's paper from '79, he indeed only invokes global symmetries. And I would say the perspective of gauge redundancy really doesn't explain, this is not Hooft naturals. You could say, all right, let's be like the Landau paradigm, let's put in gauge symmetries, it's good enough, okay. But there are many other examples, I gave you this one because it's a simple one. There's many other examples that we will encounter, just, it'll take us a little longer to develop, where it's not even gauge symmetry, but there are radially protected quantities. In some cases, we know how to explain it using things that are not symmetries. In other cases, we don't even know how to explain it. It's simply you do the calculation and you get 0, okay, and we don't know why yet. The spirit of my lectures, in part, is going to be that if we indeed formalize a broader notion of symmetry, we will actually be able to take in a lot of the explanations that we use with other means. So we will really make it fit in a Hooft paradigm. Then there will still be the things that I can't explain, okay? And that's why, indeed, this is both, this week I want to teach you about things, but then I want to invite you to take part in this great endeavor, is that we are in the process of laying out what this generalized Hooft paradigm is. Hopefully, the end point of it is we can explain the smallness of the Higgs mass and these other interesting theoretical puzzles, okay? I'm not there yet. If I were there, I would be back in my office in Santa Barbara writing the paper. But I've realized, I am limited in my faculties and abilities, and a much better thing is to recruit all of you to take part in this endeavor with me. So the idea will be to lay out, the good news is, right, the same generalizations of symmetries that have been so powerful in condensed matter physics in the last decade are also relevant to relativistic field theories. And so we can bring to bear those symmetries, generalized global symmetries in particle physics. But there have also just been other notions of symmetries that people have made more precise, especially over the course of the last decade. These include things like higher spin symmetries, and we can also bring those to bear. So the generalized Hooft paradigm, in some sense, I imagine being larger than the generalized Landau paradigm. It will include more symmetries. On the flip side, although hopefully I will show you that many more things fit into this paradigm, there will still be some mysteries, and then the question that we will end with on Friday is how we can figure out how to solve those mysteries in the same way. Okay, so the plan of attack, just to give you an outline of where these lectures will go. So for the rest of the lecture today, anytime I'm asking you to commit to understand the generalized Hooft paradigm, the first thing to do, of course, is to understand why you should have cared about the ordinary Hooft paradigm. So first, we'll just talk about the ordinary Hooft paradigm. And what I really want to do is give you actually reasons to believe that it should be true. So far I've just said some words and waved my hands at it. We'll try to formalize where this comes from. Then I want to give you examples about where it's been successful, including aspects of the standard model. And I want to give you concrete examples about where it's failed. Okay. Then we're going to start generalizing the Hooft paradigm, and so that will involve talking about a lot more symmetries that don't fit into the original paradigm. The first one that we'll talk about will be higher spin symmetry. I should say, actually, how many of you here are from Lausanne or at EPFL? Is anyone here from EPFL? Somewhat. Okay. How many of you have spent time with Riccardo Rattazzi? Okay, so what I'll tell you about, Jesse, of course, this idea actually of using higher spin symmetry to broaden what we think of as the Hooft paradigm, this really owes to Riccardo. And in fact, in his 2021 GGI winter lectures, which I encourage you to go watch the recording, that was the first time I saw him lay this out. And it's an idea that's so beautiful and interesting that, of course, I have to repeat it here. But I want to, in all fairness, point out that the gem of this idea comes from Riccardo. One thing I will do, apart from introduce it to you, is also tell you some things that it can do that are beyond, I think, what Riccardo has articulated, to really give you a sense that maybe it has some power for us. Then we'll talk about generalized global symmetries. So there are sort of three words or three phrases that will be relevant to us. There's higher form symmetries, which is the sort of core generalization of global symmetries. And then there's the things that happen to those symmetries plus ordinary symmetries in the presence of anomalies. And we get interesting higher structures that are known as higher group structures and non-invertible structures. And so higher form symmetries, higher group symmetries, and non-invertible symmetries will be what we talk about here. Just out of curiosity, so I can orient, how many of you have a working knowledge of higher form symmetries? Okay, you'll enjoy the warm feeling of hearing things you've already known, but otherwise the goal will be to teach everyone about what higher form symmetries are and what they can do for us, particularly in particle physics. And then I want to talk about some things that are not obviously symmetries, but are selection rules. So this includes so selection rules would be things, again, that govern, for example, the structure of normalization group equations. And the selection rules that we know about, there are many of the things that give rise to these examples of technical naturalness without Hooft naturalness. There is no, as far as we know, underlying symmetry that gives the selection rules, but there are things like power counting or the topology of Feynman graphs that allow us to come up with selection rules when we do calculations. So I want to tell you about examples of this, and what I would like to do, one thing I would like to do is actually try to see the sense in which some of these things can actually be fit into a symmetry-based paradigm. Okay, so I'll argue that actually some things that we say are technically natural are generalized to Hooft natural. And other things I just want to give you so that you know that they exist. They're very interesting bits of field theory, and to hopefully encourage you to think about whether we can fit them into an appropriate generalized to Hooft paradigm. Okay. So this should be ideally the first 2 lectures. This should be lectures 3 and 4, and this will be the 5th lecture. All right. So the first thing that we should do is go ahead and defend the Hooft paradigm. That is to say, we should work out why it's an interesting idea, and then we should talk about pragmatically in the real universe its successes and failures. Now, there's 2 things about the Hooft paradigm, as Hooft originally phrased it, that I want to emphasize to you, because it just helps us to think about, what it means and what it doesn't mean. The first thing to emphasize is that this is not about why a parameter is small. Right. What Hooft is saying, he's not, he's saying this parameter can be much less than 1 only if we set it to 0, we get a symmetry. So if you see a small parameter in nature, what Hooft is asking is not how was it made small, right? That's an interesting dynamical question. He's asking something like, imagine if you made it small in the far ultraviolet in your microscopic theory, how can you be sure that it should still be small by the time you get to the infrared where you're making experimental measurements, right? In this respect, Hooft naturalness, it's often, Nimar Khani Hamed often says Hooft naturalness is like a halfway house, right? If you see a small parameter in nature, if it's Hooft natural, you can believe that it survived many decades of energy. You still would probably like to explain why it got to be small in the microscopic theory, but at least you know, given that it was small in the microscopic theory, how it survived to very low energies in that shape. And the reason why I want to emphasize this point, one is it's just something useful to keep in the back of your mind about what this paradigm is, what it's asking for and what it's not asking for. So we're not always going to come up with mechanisms that make parameters small at some scale. We're going to ask, if I had a parameter that's small in the ultraviolet, how can I be assured that it's still small in the infrared? But the thing to emphasize is this really means that this is an interesting quantity for thinking about in effective field theories, right? So all theories that we encounter in nature, in some sense, are effective field theories. It just amounts to saying usually what happens, especially the situation we find ourselves in as particle physicists, we have a quantum field theory that describes nature at the scales we have access to. We know it's not a UV complete description, right? It's just an effective description. But we can still ask this question in effective field theory, right? We don't need to know the microscopic theory. We don't need to know why parameters are small. We can still ask, is it sensible that the parameters have remained small across many decades of energy? Okay. The second thing to emphasize is that parameters can break symmetries in different ways. That is to say, it's not, this is sort of an obvious statement, it's not the case that we have a symmetry if the parameter is 0, and as soon as we turn the parameter on, the symmetry is gone entirely. It's the case that, if I turn on a given parameter, given a certain symmetry, there will be some residual amount of symmetry that's left behind. There's a direction that is broken and a direction that is unbroken in the space of symmetries, and different parameters can orient themselves in different ways. That is to say, it's useful to think about parameters not as constants of the Lagrangian, but actually think about them as maybe values, background values of some field, which actually is transforming in some representation of the symmetry that we care about. So much like in the Landau paradigm, right, where the infrared of the theory was whatever survived symmetry breaking, but there was a breaking pattern where the original symmetry was broken by a local order parameter, you can think about the parameters in our Lagrangians as being order parameters. And they're the background value of some field that transformed in some way that would restore the original symmetry. All right. So this, of course, is the spirit of what's known as spurion analysis. So spurion sounds like a particle, right? The idea behind spurion analysis is that we take the parameters of our theory, which are constants, we promote them to background fields. That is to say, we imagine that they're fields. When I say background, I mean we just don't integrate over them in the path integral, right? So normally the path integral, we've integrated over all the field configurations. The thing itself is independent of the fields. But when we promote our constants to these background fields, we're not integrating over them. And so what that amounts to doing is promoting the partition function or the path integral to a function of the background fields, okay? And the reason why this is a very productive thing to do, when we promote these constants into background fields, we do so in whatever representation would restore the symmetry that we think the theory has when the parameter is 0. And the value of that is that then it allows us to trace, under renormalization, where this parameter can appear, how the symmetry breaking effects populate the different observables. Okay. Out of curiosity, spurion analysis is one of these terms of art that people toss around a lot. Does anyone know where this term originated? I don't have a guess. It wasn't Ricardo, although he's created many things. It wasn't a Ratazzi thing. So as far as I can tell, this term was invented in 1956 in the proceedings of a Rochester conference, right? In the mid-1950s, 1960s, a lot of foundational particle physics was worked out at these Rochester conferences. And they were actually basically starting to understand the theory of the weak interactions and understand various isospin selection rules. And basically, they could explain certain isospin selection rules if they if they basically introduced a spurious particle that transformed in a certain way, and then they set it to a background value. And so that was, as far as I know, the first instance of spurion analysis. But it's been something that's, of course, been incredibly powerful in particle physics, and we use a lot when we understand various aspects of the standard model. Just so I can orient myself, how many of you feel like you have a good working knowledge of spurion analysis? Like you've seen spurions before. How many of you have never heard the term spurion? Okay, good. So we're going to develop it all for ourselves. Those of you who do spurion analysis in your spare time, hopefully you'll enjoy the warm feeling of hearing something you already know. But for everyone else, we'll work out some nice examples of how this follows. And we'll really be able to use this picture to justify why the Hooft paradigm is a good idea. Okay. All right, so having made these 2 points, now I want to give you an intuitive understanding of the Hooft paradigm. And then I want to give you a slightly more formal idea of the Hooft paradigm, really grounded in the basis of spurion analysis. Before we proceed, does anyone have any questions? Okay. Actually, if you'll forgive me for using a tedious habit I have in lecturing, before I proceed, why doesn't someone ask me a question? Anything at all. It can be what's my favorite color, what's my dog's name. Take your pick. Or it could be about something we've talked about. I can stand here all day, so yeah.
What's your research?
What's my research? I'm a very broadly interested particle theorist. So what gets me out of bed in the morning is the idea that at any day we could discover the next piece of description of the fundamental theory of nature beyond the standard model. But it could be experiments that range from colliders to underground direct detection experiments to cosmological measurements. And the idea that that discovery could happen at any of those length scales means that I'm very broadly interested as a theorist. I want to sort of have an understanding of all the different possible tools that might be relevant in all those different possible ways, and to understand the ways in which tools that are developed for one problem might be relevant for other problems. So in some sense, my mind is so open that my brain often falls out, but I'm a very broadly interested particle theorist. Yeah. Okay. And that's really part of the spirit of these lectures, to tell you about new symmetries and argue for connections between them that maybe haven't been realized yet. All right. So let's just start with an intuitive explanation. So again, we've said, the Hooft paradigm is a good idea if we're talking about effective field theory. So when we're talking about effective field theory, what we imagine is we have some UV theory. So it's got some fields. It might have some heavy fields. It might have some light fields in it. And it has some parameters, right, which all denote alpha UV. So there's some set of these parameters. And then typically there's a mass scale. It could be the masses of some of these heavy particles. There could be many of them. But broadly speaking, we would characterize this as some scale. And then below that, we can construct an infrared effective field theory, which just contains the light particles. And these light particles have some parameters. They don't have to be the same in number, so I'll use an I instead of an A to index them. And of course, in perturbative completions, we can go ahead and we can carry out a matching calculation. The rules for constructing this effective field theory are that it should give you the same predictions to some order in precision for infrared observables as the microscopic theory does. And that requirement now, for example, diagrammatically in Feynman diagrams, can allow you to figure out what these parameters of the light fields have to be in order to reproduce all the predictions that come from the full theory and its full suite of parameters. Okay. Now, for our purposes, we don't need to be able to carry out this matching calculation. We just need to have this idea that if I turned these parameters to 0 and there was a larger enhanced symmetry of the theory, then when I turn these parameters on, they break the symmetry in certain directions. And if I promote them to spurions, right, as background fields that transform under the symmetry, and then maybe they get a VEV that corresponds to the measured parameter, then that means the parameters transform covariantly with respect to the symmetry that exists when we set them to 0. Okay. And so the idea we have, right, all of these parameters in the IR EFT, of course, these are just some functions of the UV parameters. And whatever the physics of this mass scale is, right, that's just the statement that we obtain these infrared parameters as functions of the UV ones by insisting that they reproduce the same observables. We don't need to be able to do this calculation, but what we need to recognize is that these transform with respect to the broken symmetries in some covariant way. And so the combinations of the microscopic parameters that can come together to make these effective parameters, they also have to transform in the same way, right? So there'll be some function for every one of these infrared parameters. There'll be some function of the UV parameters and the cutoff. And the only thing we need to know is that they have to transform in the same way with respect to the symmetries that we're breaking, okay? And from there, it's fairly simple to understand how Hooft naturalness works, right? If you knew these microscopic parameters, and again, the job of Hooft naturalness is not to explain why they're small, but simply if they're small in the microscopic theory, can we understand why they would remain small in the infrared? If you know that all of the combinations of the microscopic parameters and this mass scale that transform in the same way as an infrared parameter, if you know that all of these are small, then of course, it's only combinations of them that can appear in the infrared parameter, and therefore we can be satisfied that this too should be small. That's it. Now, you might think then, if we measure a small parameter in EFT and we see that it's small, we want to decide, is this parameter satisfying the Hooft paradigm or not? You might think we would actually need to know the parameters of the microscopic theory to make that judgment. But there's actually a fairly good proxy where even if we're only working in an effective field theory and we don't know the microscopic description, we can have a pretty good guess about what's sensible for a parameter to be small or not, even if we don't know what the microscopic parameters are. And that is to say, even if we just looked in the EFT, right, so we have this parameter, we want to know, is it natural, is it Hooft natural or not? It transforms in a certain way with respect to the symmetries that exist when we turn the parameter to 0. We know that this parameter, in truth, it's coming, really it's generated by matching to some parameters in microscopic theory. But we could also say, just in the EFT itself, right, the EFT typically has many other parameters. And we could say, look, let me make, just using the IR parameters in the EFT, let me make all of the combinations of all the other parameters, so let me call them j not equal to I, that are in my EFT. right? I should be able to take all of the other IR parameters and maybe some combinations of them transform in the same way as the parameter that I'm interested in. And now these are things that we measure. And so I can ask, okay, if I take the products of all the other couplings in the EFT that transform in the same way as the one I care about, are these numbers small or not, right? And if they're small, then it's sensible that this should be small. And if they're not, then I have a puzzle, right? Because what these are doing is they're acting as a proxy. These are also functions of the UV parameters. So in some sense, by taking combinations of them that transform the same way as the parameter we care about, we're sort of making a reasonable guess as to what the microscopic parameters would have contributed. Okay. So this is something that we do, especially when we talk about the successes and failures of Hooft naturalness in the standard model. This is really all that we can do, right? Because we've measured standard model parameters. So we can say, okay, if I'm asking about whether an observed parameter is Hooft natural, let me make all of the corresponding combinations of parameters in the standard model that transform in the same way, and ask, are those quantities of the same size as the thing I measure? If they are, we're in good shape. If they're not, there's a puzzle. All right. So we'll come back to, we'll make this concrete in a little bit. But at the intuitive level, hopefully now you get a sense of how this works. If a parameter restores a symmetry when it's taken to 0, we can equivalently treat it as a spurion, right? We can imagine that it's the constant background value of some non-dynamical field that appears in the path integral. Right? It transforms in a certain way with respect to the symmetries of the theory. We know that quantum mechanics respects the symmetries of the theory, and so it cannot be the case that quantum mechanics will generate other correlations or other effects beyond what the symmetry allows. All right, so that's the intuitive substance of the Hooft paradigm. Now, that may be unsatisfying to some of you. In particular, we're just sort of we're doing a lot of heavy lifting with the idea that quantum mechanics respects the symmetries of the theory. So now I want to give you a slightly more rigorous justification of Hooft naturalness, which again uses the idea of spurion analysis and sees the sense in which it controls the possible forms of counterterms and therefore of radiative corrections. Let's see, how am I doing on time? Okay. Does anyone have any questions about this intuitive description before we try to justify it more formally? Okay. Again, this is fairly nebulous, but yeah, when we come up with some examples of it, hopefully it'll be clear what we mean. All right. So let's try to justify it more completely. And in doing this, I'll both give you a more concrete notion of what spurion analysis means, and I'm also going to introduce a very useful tool in quantum field theory that we'll put to work when we develop generalized global symmetries. Yeah.
I was considering, what if there's a combination of parameters that is small combination, but transform as a parameter which is not small?
Well, that's okay, right? So it depends on what question you're good. So, right, so it could be, let's say I'm looking at the situation, this parameter is large, and the combinations of parameters that I can make through other things are small, right? That's reasonable, because this simply says that there is nothing from the quantum correlations between these observables where these should be feeding into this, right, by an amount that's inconsistent with what we observe. They're just subleading corrections, whereas this is coming from some pattern of breaking that's elsewhere in the theory. Now, of course, you could ask the question the other way, this is big, is it okay that these combinations are small? Then it depends on what these combinations are, right? If there's a single parameter here which is small and this is big, we've just reversed the logic and one direction is problematic. But more often than not, actually, for example, this could be a product of two parameters that transforms in the same way as this one. Each of those two parameters could also transform in other ways that are traced out as a singlet when I make the combination, right? So these two parameters could individually be protected, but their combination then transforms this way. And that's okay, right? Because these have more symmetries that protect them. Again, when we come up with very concrete examples in the standard model, this would become very apparent. Okay. All right. Actually, before I develop the more formalized understanding, just to make things concrete, I want to give you one sense in which you can use this idea of Hooft naturalness to reproduce in symmetry language what we already think of as sort of routine dimensional analysis. So this, in some sense, was the first way in which Hooft naturalness was used, although it wasn't phrased in a sense. We could take as the symmetry that we care about actually just the symmetry of dilatations, or scale symmetry. And we can ask, what does that actually imply for the natural size of parameters in an effective field theory? So what we want to do is we want to say, okay, let's imagine I have some operator in my effective field theory. So I'll call that operator O. It has some coefficient, which is, it has some dimensions in natural units. And generally speaking, of course, it's possible that the dimensions of this operator could make it scale invariant, or the dimensions of the operator could make it so that this operator violates scale invariance. Okay? Now, if it's scale invariant, there's nothing interesting for us to do. But if this operator violates scale invariance, then we can carry out the philosophy of a spurion analysis, right? And we can ask then, using this notion of the Hooft paradigm or Hooft naturalness, what is the reasonable size for the parameters in the theory based on the spurion analysis? Okay, so what's the symmetry? Again, we're going to take the symmetries of the theory when we set this parameter to 0. So let's imagine when we set the parameter to 0, the theory becomes scale invariant. So what scale transformations mean, right, is we just take the space-time coordinate and we rescale it by some constant parameter lambda. This means if I have operators that have various scaling dimensions, what the operators are going to do is they're going to transform under this rescaling in a way that depends on the scaling dimension of the operator. Okay, so here delta is just referring to the scaling dimension of the operator. Again, this is a simple notion, right, in a renormalizable Lagrangian in 3+1 dimensions. For example, operators corresponding to scalar masses have a scaling dimension of 2. Cubic couplings for scalars have the operator's scaling dimension 3. Classically, it's just the engineering dimension of the fields. All right. So we can now ask, okay, so generically speaking, right, the scale symmetry will be violated if my EFT has a scale. So for example, if there's the cutoff of the EFT, that's a dimensionful quantity, and so that violates scale invariance, right? But I can imagine, by the spirit of spurion analysis, saying, well, instead of treating this as some constant scale, let me actually imagine that it's a background field and that it transforms in a way consistent with scale transformations to render the whole theory scale invariant. So that would amount to assigning as a spurion, saying if I did a scale transformation, instead of saying this is just some constant scale that violates scale invariance, if I had it transform with 1/2 powers of the rescaling parameter, then that means, at the level of the parameter squared, then that means it would restore the scale invariance of the theory. Similarly, generally speaking, if this is not a marginal operator, this coupling also has some dimension, and that violates scale invariance. But again, we can say, let's imagine promoting it to a spurion and assigning it some transformation law so that this term in the action satisfies scale invariance. And so the transformation we would assign to it is one that would compensate the scale transformation of the operator that appears in front of with just a few extra powers, right? The few extra powers are because in the action, we're integrating over d4x. That will also transform under a scale transformation. And so that compensates this part, okay? So if the coefficient transformed in this way, and I do a scale transformation, then the combination of these two things would be scale invariant, okay? Of course, in reality, this is just some constant. It doesn't transform in any way, and it breaks the symmetry. But if we imagine that it did, we could then use the consequences of that to figure out what the natural size of parameters should be. All right. So now we can use this sort of logic that we had, right? We have, for example, the coefficient of this operator. It transforms in a specific way under scale transformations, spurionic scale transformations. And now we can ask, what are the other combinations in the EFT of parameters that transform in the same way? Okay, and that gives us a reasonable expectation. What's the sort of generic size that this thing should be, given that quantum mechanics will correlate everything that transforms in the same way with respect to the spurionic symmetry. Okay, and the things that have the same units, right? The way that this transforms is the same as the cutoff of the EFT to the 4 minus delta. Right? That's just this transforms as 1/lambda. This transforms as delta minus 4. And so if I simply had lambda to the 4 minus delta power, its transformation under dilatations would be the same as the transformation of the coefficient. And so the natural expectation then in the theory is quantum mechanics will now connect things that transform in the same way so that the reasonable size for this parameter should be something like whatever the cutoff is at the EFT, that's the only scale in the problem, to these powers. Okay. One thing that tells us, for example, when we come to the Higgs mass, and this is why the Higgs mass is a threat in some sense to the Hooft paradigm, is that the mass dimension of a mass squared parameter, a scalar mass term in Lagrangian, is 2. And so by this reasoning, the natural size of that mass parameter should be the cutoff squared, right, in natural units. And the fact that we don't see anything else around the mass of the Higgs is a sign that this paradigm is under some tension. All right. So of course, all we've done here is use dimensional analysis, right? If I told you, yeah, I've got a theory, it's got some scale, I've got a coupling constant that has some units, the only thing you could do is make combinations of the scale that have the same units, and that's all you could put in there. That's just dimensional analysis. But it's been useful for us to make the same statement now at the level of symmetries, right? To assign a spirionic transformation of the parameters and recognize that dimensional analysis is sort of enforced just by the covariance of these objects with respect to the symmetry. Okay. All right. So that's a very basic and trivial application of these ideas, but nonetheless, it already has some substance. All right. Let's go ahead now, though. Again, this idea that quantum mechanics respects the symmetries of the theory has done a lot of heavy lifting, and you might worry that it's somehow unjustified, especially when we talk about the parameters of the theory violating the symmetries. Okay. So what I want to give you now is a slightly more formal argument for why the Hooft paradigm is a good idea. And again, this is sort of like, when I make a cake for my kids, I put carrots in it, right? So they get their vegetables. So the way I'm going to make this argument, now you probably don't find the argument that I'm going to give you to be as nice as cake, but I'm still going to sneak some carrots into it. I'm going to use a method which is a very useful one, and actually which will come in handy when we talk about generalized global symmetries, which is to talk about invariance of a theory with respect to global symmetry transformations by actually introducing background gauge fields and coupling them to the symmetry currents. This is something that will be incredibly powerful when we talk about theories that have different sorts of anomalies, but it's also very useful here to see how the argument works. This may be something you've already seen in your QFT class. Typically when people learn, for example, like the Schwinger-Dyson equations, sometimes they do it by introducing background gauge fields. Sometimes they do it by making a local symmetry transformation. But if you have already seen this, hopefully you'll bear with me. But if you haven't, hopefully it's something useful to you. Okay, so let's just carry out the thought experiment. So we have some theory. For simplicity, to make the argument, let's just imagine there's one parameter that we care about that violates a symmetry. Okay, so we'll call that parameter alpha. And we imagine, there's some part of the Lagrangian that respects some symmetry G. So this is G invariant. And then we imagine we have this parameter that violates the symmetry that is proportional to some operator that we'll call O sub alpha. All right, and so of course this is G violating. All right, so to analyze the theory, what are we going to do? Well, we're going to imagine promoting alpha, again, to a background field, so something that can transform with respect to the symmetry G. And we're going to assign, if we do a G transformation of the theory, we're going to assign the charges to alpha so that the total transformation of the product of alpha and the operator it's proportional to, that this variation vanishes, right? Of course, normally, if this is just some constant, it would be the case that if we did a G transformation, this operator would transform non-trivially, and there would be some contribution to the variation of the action that would be non-zero. But we're simply going to carry out the thought experiment that we've promoted this actually to a background field, and we've given it whatever transformation properties it requires so that this product is now invariant, okay? And again, I want to emphasize the one thing that's important to keep in mind when we promote this to a background field is we're not integrating over it in the path integral. Okay, we're integrating over all the actual fields, but we're not touching this. All right. So once we've promoted this to a spirion, now actually the entire action is invariant under G. And now we want to work out what's the whole purpose of this endeavor. What we would like to see is the following. That when we actually go ahead and normalize the theory, right? So when we let quantum mechanics, generate correlations between parameters, because renormalization is what correlates different quantities in a quantum field theory. What we would like to see is that once we even construct the renormalized theory, the counter terms that we can introduce to absorb the divergences, which govern the beta functions and the anomalous dimensions, they tell us how everything is connected. that those necessarily, the ones that violate the symmetry, have to be proportional to the symmetry breaking parameter itself, right? If that's true, then we can understand why this parameter could remain small as a function of scale, because it would be renormalized only proportional to itself. Or if there were multiple terms that transform in the same way, it could only be renormalized proportional to the things that transform in the same way. All right, we'd like to make that argument formal. All right. So how are we going to do it? So we've said once we make this spironic parameter transforming to make this term invariant, we now have an action, actually, that in this thought experiment is invariant. And the way to make that substantial is we're going to trade invariance of the action with respect to that symmetry once we have this spurion. We're going to exchange that by saying, well, if it's a good symmetry of the theory, then I should be able to gauge it, okay? Right, I should be able to couple a gauge boson to the conserved current of the theory. And indeed, Hooft's original reasoning in a different set of papers was that you really can't tell the difference between a very good global symmetry and a gauged symmetry with a very small gauge coupling. So I should be able to go back and forth between thinking of a global symmetry or gauging the symmetry with a very small coupling, okay? So the way we're going to do it, so this original theory, which is G invariant, this has some conserved current in it, right? Let's just imagine it's a continuous symmetry, so there's a Noether current. To probe what it means for this theory to be invariant is we're going to imagine now gauging the symmetry, okay, which says in the action, we're going to introduce another background field, which is a gauge field, and we're just going to couple it to the conserved current of the original theory. Okay? And the idea is, right, that I can now trade conservation of that current for invariance of the action under background gauge transformations. So if I took a gauge transformation that takes this gauge field and shifts it by the derivative of a gauge transformation. Oh, sorry, I should use a different thing, not alpha, that's our bad parameter. Let's call our gauge transformation parameter lambda, okay? If I did a gauge transformation of this background field, all right, G invariance of the action, conservation of its current, is equivalent to the statement that the action is invariant under the gauge transformation. And that's fairly simple to see here, right? If I did this gauge transformation, the variation of the action would go like the integral d4x, and then now I would have the variation of the gauge field. So that would give me d mu times the transformation parameter, and this would be multiplying j mu. But now if I integrate by parts, right, this is just minus the integral d4x, the gauge transformation parameter, and the divergence of this current. And so if this current is conserved, right, this vanishes, that's equivalent to saying there's no variation of the action with respect to the background gauge transformation. So it's very useful if you have a conserved global symmetry in your theory. If you want to probe the consequences of that for correlation functions, one way to do it is to say, let me imagine gauging that symmetry by coupling it to a background gauge field, and then trading conservation of the current for invariance of the action under the background gauge fields. Okay. So we're going to use that momentarily, but I want to emphasize this is going to be good for what we're about to do, but this is also great for the understanding of certain types of anomalies in quantum field theories, and so we're actually going to use the same trick over and over again in the next few lectures. All right. Does anyone have any questions? I know I have two different types of background fields now, right? We have our coupling alpha that violates the symmetry. We've promoted that to a background field called a spurion. And then I've said we also want to understand invariance of our theory under G transformations by coupling the conserved current of the theory to a background gauge field and then imagining doing background gauge transformations. So there's two different background fields. They're doing slightly different things, but they'll help us to understand why it is that if a parameter violates a symmetry, it can still be small at low energies. Yeah.
In this case, we are always thinking about lows just somehow, right? Because for example, from the scaling variable.
Yes, yes. So this argument, indeed. So here, in my attempt to justify sort of more formally how sort of Hooft paradigm works, I'm just thinking about a global symmetry that is a continuous symmetry, so it emits a Noether current. Using this particular logic that I'm about to use on symmetries that are not continuous global symmetries is more complicated. I'm not going to attempt to justify it with respect to dilatations or with respect to the higher spin symmetry. You may know, as you may know, like coupling background fields to those quantities is a much more complicated endeavor. So I'm not going to use it to justify that. But I would like to justify the global symmetry case. Part of it is that we go around invoking Hooft naturalness all the time. It has thousands of citations. Nobody actually pauses to sit down and ask, why does it work apart from this sort of hand-wavy heuristics about quantum mechanics? So I would like to do a little bit better. Okay. Good. So what do we have? So we imagine, again, something I want to emphasize as well, the current that we're coupling this background gauge field to, so we exchange conservation of the current for invariance with respect to background gauge transformations. This is the conserved current that's part of the good part of the Lagrangian, right? The part of the Lagrangian that is invariant under G without having alpha turned on, okay? We don't have terms in this current that depend on the spurion alpha, right? The spurion alpha is a background field, okay? So this is just an important distinction to keep in mind. And we know once we've turned alpha on, right, that this current would no longer be divergenceless, right? It would have something that's proportional to that operator and to alpha. Okay. So now what are we going to do? We're going to use the fact that we know, so now the path integral is a function of two things, right? We've integrated over all the actual fields. But now it's a function of the spurion, which is a background field, and it's a function of this background gauge field coupled to the conserved current, okay? But now we know, so now we're going to do a gauge transformation, okay? And so that means that both the spurion is going to transform, right? Because we said the spurion, we assigned it some transformation properties under the symmetry G to make the whole action invariant. When we gauge that symmetry, that means we should think about, under a gauge transformation, all of the things that transform under the gauge symmetry transform. So the spurion would have some transformation. And of course, the background gauge fields would have some transformation, which is literally just an ordinary gauge transformation. Okay? But now, because we have chosen the transformation properties of alpha to make G a good symmetry of the entire theory. And if we have a good global symmetry, though we have invariance of the path integral under background gauge transformations, that means under this gauge transformation, the path integral is itself going to be invariant. Okay? All right, so equivalently, the variation of the path integral or any of the things that we derive from it. So for example, the generating functional for connected correlation functions or the 1pi effective action, all of these things will be invariant with respect to this background gauge transformation. And then we can put this to work. So one way we can put this to work is we can say, okay, let me actually construct this transformation in the action and expand it to first non-trivial order in the gauge transformation parameter, okay? What that actually will give me is a ward identity, right? So something that holds relating operators inside a correlation function. The ward identity, so the first variation, if we just take the first variation with respect to this transformation and recognize that that has to vanish, that's going to tell us an interesting combination of operator relations hold inside correlation functions. So there's going to be one piece that comes from the variation of the gauge field, and there's going to be one piece that comes from the variation of the spurion under the background gauge transformation. And these things are going to add up to 0, right? This is just the statement that the first variation of the path integral with respect to the gauge transformation vanishes. Okay. But now you may recognize this quantity inside correlation functions. This is just what we mean, right, by the insertion of the conserved current J mu, right? Because if I take, sorry, I've written it in terms of the generator of connected correlation functions. This just could be Z. So A mu only appears coupled to J mu here, right? So if we took the variation with respect to A mu, we would just be pulling down a factor of J mu inside correlation functions, okay? And the second thing, right, this is actually, for a similar reason, this is just an insertion of the symmetry violating operator, O alpha, right? Because the parameter alpha appears just proportional to this. And so if I took a variation of the path integral with respect to alpha, I would just be pulling down a factor of O alpha in correlation functions. So this is a word identity that we're simply getting from invariance with respect to background gauge transformations. But it reproduces inside correlation functions the thing that you already believe to be true, which is that we have a current that's constructed out of the good part of the theory. I also have an operator that violates the current. And so the divergence of the current now is no longer 0, but instead it's proportional to the symmetry violating operator. Right? That's just being now reproduced in this nice way inside correlation functions. Okay, so this is one way. Hopefully you believe these background gauge fields are a handy trick. We just had to couple them to the symmetry of the theory, do a background gauge transformation, and out pops a word identity, which tells us about violation of the symmetry inside correlation functions. But let's also use it to say something about the renormalization of the theory, right? Again, the whole thing that's been doing the heavy lifting when we talk about Hooft naturalness is quantum mechanics respects the symmetries of the theory, and so only things that transform in the same way as our spurion can renormalize it. We should now be able to see that more concretely. Okay. So the way that we can see it, right, if we think about renormalization, we can construct, here I'll call this the bare path integral. All I really mean is this is the path integral carried out with the bare Lagrangian. As we know, right, we can write this when we actually go ahead and compute it at whatever loop order we want to. It will have two pieces. It will have a finite piece, and it'll have a divergent piece. And to renormalize the theory, right, to get the renormalized action, we introduce some counterterms, which help us to accommodate the divergences that appear in the divergent part of the action. So we know, again, if we do this background gauge transformation, the left-hand side is going to be invariant, right? That certainly means that the sum of terms that appear on the right-hand side will also be invariant under the background gauge transformation. But on top of that, it actually means that they will individually be invariant under the background gauge transformation. And the reason for that is that, right, we've partitioned this into some finite piece and some divergent piece. There is nothing that the finite piece could do, right, to cancel things appearing in the divergent piece. So it must be the case that under background gauge transformations, the divergent piece itself is invariant, okay? But this is an important distinction, right? Invariance of the whole bare quantity under the background gauge transformation. It could have been the case that even if I'd split it into two parts, they compensate each other to make the combination invariant. But because in this case, one is divergent and one is not, they can't help each other out. And so each must individually be invariant, okay? So this is a super powerful statement, right? It tells us that the divergences of the theory, okay, which we will control by adding counterterms, and those will tell us, you know, what the beta functions are for the usual procedures in a field theory. This thing alone is invariant under the background gauge transformations, okay? There's one more piece of information that's useful to us, which is, you know, a result that is attributed often to Weinberg or to other results in axiomatic field theory, which is that the divergences of the theory can be absorbed by local counterterms. Now, this is something that we normally prove in perturbation theory, where we say if you have a Feynman diagram and it has a divergent piece to it, that's actually originating from some subdiagram. And it turns out you can prove that those subdiagrams are polynomials in the external momenta, which means they correspond, once we want to absorb the divergences, to insertions of local operators. Okay, so that's the one more fact that we're going to use, which is that if we want to renormalize the theory and absorb the divergences that are showing up here, we're going to do it by introducing local operators. All right. And actually now, that means we're done. Because now when we want to absorb the divergences that appear here, right, we're going to do so by adding some counterterms to our Lagrangian. Those counterterms, right, will have the form of some sum over some coefficients times some local operators. And those local operators, their structure is governed by whatever the divergences are that we want to cancel. But now we know this whole thing is invariant under background gauge transformations. So that means this whole thing is going to be invariant under background gauge transformations. It's also, of course, going to be a function, right, of this spurious parameter that violates the actual symmetry G. So now this allows us to trace how our symmetry violating parameter gets renormalized, okay? Because all of the terms, the combined terms here on the right-hand side, they are all invariant under this background gauge transformation. Now if we go ahead and we say, okay, let's now end our thought experiment that alpha is a background field transforming with respect to a gauge symmetry, let's instead just say, all right, now alpha is whatever constant is in nature, the symmetry is broken, right? We can now we've controlled exactly how that parameter can appear in the counter terms, right? Because all of these things had to be invariant with respect to the spurionic symmetry, okay? When we set this thing to a constant, now that means that this has terms in it that violate the symmetry. But the local operators that appear to give us the counter terms, if these transform non-trivially under the symmetry, they have to appear with whatever powers of alpha made the combination invariant, right? That's what background gauge invariance gave us, okay? So that means there's no way that I can generate terms in the counter terms, which will tell me about the beta function. There's no way I can make counter term operators that violate the symmetry without being proportional to the symmetry violating parameter itself, okay? And of course, if I had multiple symmetry violating parameters, then the only counter terms that could appear here would have to be proportional to the appropriate combinations of the symmetry violating parameters. So this is the sort of much more concrete and hopefully satisfying version of the hand-wavy argument that quantum mechanics respects the symmetries of the theory, and therefore a spurion transforming in one way can only get quantum corrections proportional to other combinations that transform in the same way. We've now guaranteed that that's true using a little bit of knowledge of perturbation theory, particularly the structure of local counterterms, but maybe in a more systematic way. Okay. And so, of course, then if you went ahead, right, the structure, which introduced the counterterms, now we can use this to compute the beta functions. And this will tell us things like, the beta function of this symmetry violating parameter itself. This has to necessarily be proportional to the parameter itself times some numbers. Or again, if we have multiple couplings in the theory whose product violates the symmetry in the same way, they can also appear on the right-hand side. But it has to be covariant with respect to the direction in which we violated the symmetry. Okay, so this is hopefully a more satisfying justification of why Hooft naturalness is a good idea. That's just grounded in the idea that the divergent structure of the field theory is what tells us how quantum mechanics relates different parameters. We've shown why it is covariant. And the other thing that we've done is we've introduced a very handy method of seeing it, which is whenever we have a global symmetry, we exchange conservation of a symmetry current for invariance of the action under a background gauge transformation. And again, that's something we'll make use of later. Okay. So we've made some effort to justify, oh good, I'll get you in 1 second. We've made some effort now to justify why the Hooft paradigm is a good idea. What I want to do next is actually build, it's one thing to say some abstract theoretical argument by something should be true, but everyone has a plan until they get punched in the face. And so you would like to go out in nature and say, like, does this really work? And so the next thing we should do to really build our confidence is see the sense in which this example, these ideas of spurion analysis are very powerful and validated by experiment. But before I do that, you had a question.
Question regarding the finite number of local counterterms.
Yeah.
It seems like the original Lagrangian has a term that is a singlet under the global symmetry. For any counterterm we have, you can multiply that by the singlet term, and that would give you another counterterm.
But that's absolutely, oh, sorry, you good. I haven't assumed renormalizability. Of course, if I've assumed renormalizability, we know it will be the case that the divergences at a given loop order can be absorbed into a finite number of counterterms. So multiplying by powers of a singlet operator will simply take us out of the renormalizability criteria. If we were operating an effective field theory, which formally has an infinite number of counterterms, what we usually mean when we talk about an effective field theory is that the effective field theory is power counting renormalizable, which is at a fixed order in power counting, there's a finite number of counterterms that can absorb all of the divergences. So I'm assuming that here. Okay, let's also assume that our EFT is power counting renormalizable. So that it means it has an infinite number of counterterms, but at a finite order in the power counting, There's a finite number of them. Okay, but the fact that I'm dressing any counter term with a singlet doesn't change. That didn't really matter for the thing that we care about, right? The thing that we care about is once I set the spurion to its background value, there will now be non-invariant terms that appear in the counter terms, but they can only ever appear proportional to the spurion itself, and that doesn't matter if we dress them by high powers of the singlet. Right? Great. Is that satisfying to you? Great. Okay. All right. So now let's go ahead and actually come up with some concrete examples for why this is a good idea. And indeed, it's these sort of concrete examples that Hooft had in mind when he wrote his original paper. I do encourage you all to go read his original 1979 paper because it has a lot of interesting ideas, not just about this principle, but also about sort of properties of quantum field theory as they were understood at the time. All right, so the place where this really comes to life is when we think about the effective description of QCD at low energies, when we enter into the chiral Lagrangian, right, our description of the low energy degrees of freedom in terms of mesons and baryons. So it sounds like only a few of you have seen spurions, so it may be that how many of you actually have some exposure to the construction of the chiral Lagrangians from the symmetries of QCD? And how many of you have never been exposed to that? Okay, well, I will try to say enough that it's still useful to you, but I'll also go through it quickly enough that we can get to the substance of the spurion analysis. Okay, so let's think about QCD, as Jesse helpfully introduced to us this morning. We're not going to think about QCD in its full generality. We're just going to zoom in on the energy scales close to a few hundred MeV, where, of course, QCD confines. And we know as we go well above the confinement scale, QCD has the famous property of asymptotic freedom, which is that we can describe it in terms of some weakly interacting degrees of freedom, the quarks and the gluons. And what we're interested in doing is saying, all right, we have sort of ordinary QCD is our UV theory above the scale of confinement. And below the scale of confinement, we see mesons and baryons. So crucially, we see things like the charge and neutral pions and the kaons and all that whole other zoo of color singlet bound states. And what we'd like to do, right, is we say that we know the theory of QCD, and we'd like to do our very best to figure out what we can say about this low energy effective theory, the chiral Lagrangian. And of course, the term that we use for it, the chiral Lagrangian, should already be a sign that the way we're going to make this connection is by using the symmetries of the theory in the language of effective field theory. So for our purposes, we're just interested in zooming in on the low energy degrees of freedom. So we're going to ignore most of the heavy quarks, right? They have been integrated out well before we get down to the confinement scale. And so for our purposes, for simplicity, we're only going to consider the two lightest quarks, the up and the down quark, right around the scale of QCD confinement. And so our very simplified version of QCD for this argument is just going to say we have two quarks, the up and the down quark. And if we only were paying attention to QCD, right, if we ignored electromagnetism, we've already broken the weak interactions, let's even ignore the fact that the up quark and the down quark have unequal masses, then just staring at them, we have these two quarks, which are both charged in the same way under QCD, and so there's a symmetry that allows us to rotate them into each other, okay? And we can actually do this both for the left-handed components, right, which we get maybe by doing a left projector on the Dirac fermion. And we also have this for the right-handed components, which we get by using a right projector on the Dirac fermion. And so actually the symmetry, once we combine QCD plus the space-time symmetry, now we can rotate the left-handed components of U and D into each other and the right-handed components of U and D into each other. And so that means there's a symmetry of the theory, which is the rotations of the two Weyl fermions UL and UD into each other. So that's a full U2. And then the same rotations of the UR and the DR into each other. So that's a separate U2. Okay. Now, what we normally do as particle physicists, right, is we recognize anytime we have a UN symmetry, we can productively break that into a U1 symmetry and an SUN symmetry. So we're going to do that here. We're going to throw away or at least ignore the U1 factors. We'll come back to those when we talk about anomalies. But for the time being, we can just chuck them out. And so we can really just afford to focus on the SU2 symmetries that correspond to the rotations of UL and UD into each other, UL and DL into each other, and UR and DR into each other. All right. So these are the global symmetries of our QCD theory. If we ignore, of course, electroweak interactions and we ignore the masses of the quarks. Okay. So the QCD Lagrangian with these assumptions, right, we've got kinetic terms for the left-handed and right-handed components. And then we have one more thing, which is we actually do, once we've broken electric symmetry, have masses for the up quark and the down quark. And so we'll have to include also a mass term, which mixes the L's and the R's. OK. So that's our UV theory. If we ignore the mass terms, we have the symmetry of separately rotating the left-handed components and the right-handed components to each other. If we turn on the mass terms, right, this mass matrix in this space is diagonal, but with unequal entries. That, of course, will eliminate our freedom to make separate rotations of the left-handed and right-handed components into each other because it correlates them, but in a way that we can track. All right, so that's our UV theory. With malice aforethought, this mass parameter is violating a symmetry, and so we're going to treat it ultimately as a spurion, and we're going to use spurion analysis to figure out how this explicit breaking of these SU2 symmetries percolates from the QCD theory through strong coupling down into the low energy effective theory and the chiral Lagrangian. All right. Before we even do that, it's worth pausing. We already get something in QCD from the observation that if I didn't have the mass terms, the theory would have this global symmetry. And if I turn on the mass terms, I break this global symmetry. Right? That tells us that the quark mass parameters are radiatively stable. Okay? It's not, they're Hooft natural. We don't have a problem understanding why they're small, because if I set them to 0, they enhance the symmetry of the theory. Okay, so this is, of course, the famous chiral symmetry, which allows us to understand many properties of QCD. All right. But where does the spurion analysis really come into handy? It comes in handy when we want to go ahead and match this ultraviolet theory down into the infrared, our effective description that describes the mesons of the theory. So, of course, the hypothesis is that in QCD, right, when the strong interaction grows strong, it gives a vacuum expectation value to quark bilinears. And that vacuum expectation value spontaneously breaks this SU2 left cross SU2 right symmetry to a diagonal vector-like combination. All right, so this is confinement. And so by hypothesis, this is the VEV of some quark bilinear. All right, so much like the Landau paradigm, in this case, we are able to classify the phases of QCD matter by the symmetries that they break. And crucially, right, because we've spontaneously broken a global symmetry of the theory, if we ignore the masses for now, that means there should be Goldstone bosons. How many Goldstone bosons should there be? Some gang signs, 3, okay. There should be 3, right? That we have the Goldstone bosons, number of Goldstone bosons equal to the number of broken generators. Each of these has 3. This only has 3 itself, so we have 3 broken generators, and so there'll be 3 Goldstone bosons. And so using the philosophy of effective field theory, what are we going to do? Well, by hypothesis, again, the effective field theory will consist of the low energy effective degrees of freedom, the Goldstone bosons. They necessarily, by construction, transform appropriately under the underlying unbroken symmetry of the theory. And the effective action that we construct out of them, the chiral Lagrangian at low energies, will simply consist of all of the terms that are consistent with that symmetry that involve the Goldstone bosons. Okay. And so the way that we do that is we construct a field that involves the Goldstone bosons. The Goldstones, of course, transform non-linearly, but we can package them in a useful way into an object that will transform linearly if we did these underlying global symmetry transformations. So the combination of the Goldstones that will allow us to do this, of course, is a familiar exponentiation. Here are the pi's of the Goldstones. They're going to appear contracted with the corresponding broken generators. And then there has to be some normalization, which we call the pion decay constant. All right. And so the idea is the Goldstones are transforming in a way that's governed by the symmetry breaking pattern. When we make this combination of them, we arrive at a field which transforms linearly. And so if we did an SU2 left and SU2 right symmetry transformation, then this field would transform from the left by the SU2 left transformation and from the right by the conjugate of the SU2 right transformation. Okay, so this is how this field transforms. And the idea then is we should simply now construct an effective description, which will give us the EFT, which consists of all of the possible combinations of this field that transform invariantly with respect to these SU2 left and SU2 right transformations. All right, again, for those of you who are familiar with this, I apologize for making you go back through it, but it's always useful to remind ourselves how this works. All right. Something else that's worth noticing, I should say, by the by, if we make a combination of U dagger U, that certainly is going to be, if we take the trace of it, or traces of these products, this object is necessarily going to be invariant under the SU2 left and SU2 right transformations, but this is also going to be proportional to the identity because this U field, which transforms linearly, is e to the I something, right? Where these are now real objects. So if we took its Hermitian conjugate and combined it with itself, we would get the identity in this space, okay? So that already tells us something interesting. When we construct this effective action of the Goldstone fields, in order to pick up something that's not trivial and is invariant under the symmetry transformations, we're going to have space-time derivatives, okay? This reflects, of course, the fact that the Goldstones are Goldstones and that they enjoy a shift symmetry. So the derivative coupled nature of the effective action is necessarily reflecting the fact that they're Goldstones. Okay, so if we want to write down the effective description following our rules of putting all of the terms that are invariant under the SU2 left times SU2 right symmetry constructed out of U, the first non-trivial thing we can write down, of course, it has some normalization, which we've chosen just to give canonically normalized kinetic terms, and it's just going to be a trace of derivatives of this U field and its conjugate, right? So if we go ahead and expanded this out, right, in terms of the Goldstones, we would get canonically normalized kinetic terms for the Goldstone fields, plus we would have a whole tower of higher derivative interactions from the higher term expansion of the exponential. All right, that's all fine. But again, when we've done this, we've assumed that this is an exact global symmetry, and then we've written down an effective theory which preserves that exact global symmetry, albeit spontaneously broken. So now we have to face the music, right? And we have to realize that this is not an exact symmetry, but instead it is a symmetry which is broken by the non-zero masses of the up and the down quark. So rather than throwing up our hands in despair, we pull out our favorite friend, the spurion analysis, and we say, okay, we know what to do, right? Let's promote the mass of the quarks to a spurion. Let's assign it a transformation with respect to SU2 left and SU2 right, so that the mass term in the Lagrangian is invariant. And now it is a new ingredient that we can take down into our effective theory, which transforms non-trivially, and I can construct new invariants in the effective action involving this parameter that controls how the parameter appears. Then we'll set it to its background value, and we'll come up with a prediction for the masses that should be generated for the Goldstone bosons that feed off the masses that originated with the quarks. Okay, so we can do that easily enough. We can see the way in which these mass terms violate the SU2 left and the SU2 right symmetry. So without assigning this any spurionic transformation parameters, if we did an SU2 left and SU2 right transformation, this here, the Q bar L, would pick up a factor of L dagger acting on the right, and QR would pick up a factor, so that's the SU2 left transformation parameter. The SU2 right transformation parameter, R, would pop up here. Okay, that clearly would leave this term non-invariant, and so we would have a problem. So we simply recognize that if we ask that the mass matrix transform by L on the left and R dagger acting on the right, right, then that would give us an L here and an R dagger here, and since these are unitary transformations, they would go away. All right, so that would restore invariance with respect to SU2 left and SU2 right, using our spurionic prescription, where we now treat this as a background field that transforms in a way that restores the symmetry. Okay, so that's our spurion assignment. Now we take it back over here, and we say, okay, we can also use this now as an ingredient in the effective theory. We can now write down additional invariant terms in the effective action, which simply use powers of the spurion to compensate for the transformations of U. Okay. So this now allows us to write down a new term, we'll add, again, the pion decay constant for convenience. And it has some independent coefficient that I'll just call B. And the new invariants I can write down are traces of the mass matrix and U conjugate, and for hermeticity, the conjugate of the mass matrix and U. Of course, I can write down more irrelevant operators, but this is a leading non-trivial one. These combinations now are also invariant under the SU2 left and SU2 right symmetry transformations. So what I've done is I've figured out, even though I absolutely have no idea what happens when QCD confines, how to make the map between the quark degrees of freedom and the pions, right? I have no ability to do a matching calculation in perturbation theory. By doing a spurion analysis, right, I can figure out how the mass matrix that violates the global symmetry should appear in the effective theory. And now I can go ahead and say, great, I figured out how it can appear. Now let me end the charade of my spurion analysis. I'll set it to its background value, where it's proportional to the quark masses. And now I can figure out, by expanding these exponentials, what the masses of the pions are. Okay, and so of course, when you do this exercise, so you expand out the U's, and you can construct the combinations of the pions that correspond to the charge in neutral pion, you find that the pion masses squared are just proportional to this coefficient B, and the combination M up plus M down plus some higher order bits. And so that's a beautiful result, right? One of the things that's beautiful about it is it tells you how, in some sense, this is the thing we measure, right? We actually measure the masses of the pions. So we can now use this to infer, in some sense, pieces of the underlying theory that we actually don't have access to directly. We, of course, absolutely don't measure the pole masses of up and down quarks. But now, by having this relation and more elaborate versions of these relations, and taking all of our measured data at low energies, we can use this, to get a fairly good idea of what these masses are of the quarks, even though we never see that directly. Okay. We also have an interesting prediction that it wasn't obvious from first principles. We know the pions are Goldstone bosons of the spontaneously broken symmetry, but it's not obvious just by staring at it that once we turn on quark masses, the masses for these pions should be the same. And at leading order, we see, in fact, that they are. Okay, so there's very powerful things that come from using a spurion analysis. So it was the success of this kind of thinking, right, that really animated Hooft when he first formulated the Hooft paradigm, that by taking symmetry-violating parameters, promoting them to spurions, and then following them through, recognizing that the theory has to transform covariantly with respect to the spurions at all scales, okay, then you can actually make beautiful predictions in an effective field theory, even when you can't do a matching calculation. On top of that, you can see how in the UV theory, we don't worry about the fact that quark masses are small, because asymmetry is restored when they go to 0. And we can also see that even though incredibly violent processes like confinement happen as we go to the infrared, that still controls in a very nice way the way that those parameters should show up at long distances. Okay, so that's a really good example of the success of the Hooft paradigm, both the idea of reasoning in terms of spurions and in terms of being able to track quantities through violent processes such as confinement. Okay. Let me give you one more argument, which is not unrelated actually to the naturalness of the Higgs parameter, which is again a success in the chiral Lagrangian of thinking about spurions. And then I think probably we can close for some questions and discussion, and we'll pick up the successes and failures of the standard model at the start of the next lecture. So of course, in this very nice discussion, we've said, I said, let's just consider QCD and let's ignore the electroweak interactions entirely, right? We just thought about SU3 color and the quark degrees of freedom, and we traced them down to the IR. But of course, we shouldn't really have done that, right? We also have, for example, even at the scale of QCD confinement, we have electromagnetism. We know the quarks are charged under electromagnetism. And the electromagnetic charge assignments of the up and the down quark, they happen to violate also the chiral symmetry, right? So just the fact that the up quark and the down quark have different charges means the charge matrix for the up and the down quark in this space is also diagonal but not proportional to the identity. So electromagnetism violates the chiral symmetry. But now we can do something incredibly powerful. We can continue to use the spirit of spurion analysis. I'll just tell it to you at the word level in the interest of time and get to the punchline. But the idea is we can now add electromagnetism, so we can turn on the photon, and we can couple it to the quarks. We can now recognize in the space of SU2 left and SU2 right, there's now another object that violates the symmetry, which is the charge matrix for up and down. But we can go ahead and we can promote that to a spurion. We can again assign it spurious transformation properties so that electromagnetism with the spurious transformation restores the symmetry. And then we can use that to actually trace then how electromagnetism should appear down in the chiral Lagrangian with the exact same procedure that we've used here for the masses. Okay? So now we can write down extra terms in the action, which involve the effects of electromagnetism. They have to be proportional to the square of the electromagnetic coupling because that appears in the spurions, and it's entirely governed by the spurion analysis. What the effect of this is, a couple of things. One is it's something that we've already taken for granted. We said that the goldstones that we have at low energies arrange themselves into a neutral pion and a charged pion. Doing the spurion analysis, in fact, tells us that was the right thing. The way that the photon couples to the low energy degrees of freedom, which we obtained by following the spurion analysis, tells you the photon now couples with unit charge to these charged pions and doesn't talk to the neutral pion. It does one more thing, which is, I think, a very beautiful demonstration of the efficacy of the Hooft paradigm. And so maybe let's do this before we end, which is actually allows us to make a very simple check whether this natural reasoning works when we talk about mass parameters in the presence of explicit violation of the symmetry. So at the level of the analysis we just did, right, we said quark masses leave a degeneracy. They give masses to the pions, but they tell us that the charge and neutral pions have the same mass. But if we turn on electromagnetism and we follow it down to the chiral Lagrangian with the spurion analysis, we now see that electromagnetism, of course, distinguishes the two. Okay? The photons couple to the charged pion and not to the neutral pion. And so now we can ask, all right, in the effective field theory, let's just go ahead and compute some Feynman diagrams. And we should see if we can come up with an estimate of the shift in the pion masses that are induced by the coupling to electromagnetism. Okay? Because again, crucially, because electromagnetism violates the shift symmetry that protects the pion masses, it necessarily can give contributions to those masses in the EFT. So there's a diagram which contributes to the mass normalization of the charged pions. You can have charged pions flying through space. And then, for example, you can have a Siegel diagram where you just have a loop of a photon. All right. There is no corresponding diagram for the neutral pion, right? The neutral pion is just merrily flying through space, completely ignorant of the existence of electromagnetism. And you can say, okay, let me at least estimate the size. So this is a divergent diagram, but we're in an effective field theory with a cutoff. So let's say, let me just estimate the size of the mass correction that this should give to the charged pions. Now, already, just using the spurion analysis that we've developed, we know that if I wanted to make a contribution to the charged pion masses, this is going to have to transform with two pieces. It's going to have to transform with something that goes like the square of the electromagnetic gauge coupling. That comes from doing the spurion analysis for electromagnetism in the chiral Lagrangian. And then from our dilatation analysis that we carried out, this is a mass parameter that has mass dimension 2. And so if the only other scale we have in the problem is the cutoff of our EFT, it has to go like lambda squared. Right? So just using spurion analysis at the level we developed it, we already have this expectation. So now we can go ahead and we can check the extent to which this is justified just by saying, okay, I can actually calculate this diagram, right? I know what this coupling is because it's governed by electromagnetic symmetry. So this goes like E squared. There's going to be a loop factor. So this is a correction to the charged pion mass. So it's going to go like E squared. There's going to be a loop factor. And then if I just do this with a hard cutoff, this is a quadratically divergent diagram, and so it's going to be proportional to the momentum cutoff of the theory. Okay. If I do it carefully, all right, there's a factor of 3. But just doing Feynman diagrams by eye, it's good enough to give us the most important properties. All right, so this is just from the EFT, given how electromagnetism violates the shift symmetry, this looks like a correction that we should pick up to the charged pion mass, which is not experienced by the neutral pion mass. And now we can go ahead and ask, how much is nature, adhering to these naturalness principles that we espouse? This is now a contribution to the mass of the charged pions. It's not a contribution to the mass of the neutral pions. And so, at least at the order of this calculation, what this tells us is we have an interesting prediction in the EFT for the mass difference between the charged and neutral pions, which is precisely this quantity. Now, these are also things that we can go ahead and measure in nature. So if we go ahead and measure this quantity in nature, it turns out that this difference between the squared masses is about 1.3 times 10 to the 3 MeV squared. Okay, so that's the experimentally measured value. And now we can say, all right, the idea is, right, we have a calculable correction to this mass splitting, which is given to us by our symmetry considerations. If this is what's explaining the observed mass splitting, we know this quantity, so we can ask, all right, what should this quantity be? So we can go ahead and divide this by that, take the square root. And what this suggests is that the cutoff should be approximately 770 MeV. And so, sure enough, as you go up in the mass scale of the bound states of QED, of the Carl-Lagrangian, something happens when you get around 770 MeV. Does anyone know what particle you see, what bound state of the strong interactions you see around the scale? What's that? The rho, right? So you actually see the first vector meson excitation, which is a sign in some sense that our calculation of the vector excitations of the theory, which just had the photon in it, is incomplete, because there's actually some extra contributions from the rho, which regularize this contribution from QED, and indeed furnish the cutoff that we've seen in our effective field theory. So this is an insanely successful triumph, right, of the Hooft paradigm. We're in a situation where we have a calculable microscopic theory, then we have strong coupling phenomena, and we have an effective description, which is what we're actually measuring in data. We were able to use symmetries to govern how the breaking of the symmetries in the microscopic theory percolate in the effective description at low energies. We were able to do a calculation that effective field theory, right, again, governed by the spironic violation of the symmetries, to make a prediction, which was related to an observable. And then the expectation, right, that the thing that had the right symmetry properties to appear in this difference not be dramatically different from what we measured turns out to be wildly successful, right? It is bang on the appearance of a new degree of freedom, which is the physical manifestation of this cutoff. So, at the end of these lectures, at the level of where we're at, right, the level of understanding QCD at low energies, the Hooft paradigm is insanely successful. Right, we take this for granted, okay, whatever, it's some QCD standard model physics, but this is amazing, right? And so, this is why for decades, despite its observed challenges and theoretical challenges, the Hooft paradigm has held such sway, because in this very complicated environment, it works more beautifully than you could have ever imagined. So I think that's where we'll leave off for today. Where I want to pick this up next lecture is then to zoom out and focus on the entirety of the standard model. And we can say, okay, we have all the fields of the standard model. We have all of the 19 free parameters of the standard model. We can go ahead and ask the extent to which the measured values of the parameters and the symmetries they violate are consistent with the expectations from the Hooft paradigm. And of course, the answer is many of them are very consistent. Some of them are very not consistent. So then we're going to zoom in on the ones that are not consistent and see how much we can understand by extending the standard model. I'm going to do that very briefly. This is not going to be a set of lectures about supersymmetry or composite Higgs models, but at least we'll say those words and see how they connect to the paradigm of Hooft naturalness. But at that point, I want to just focus on, given the many failures of the Hooft paradigm that we see in the standard model and in theoretical calculations, what is the much broader space of symmetries that we should allow ourselves to think about? And if we bring that broader space of symmetries to bear on these problems, can we actually understand them in a much more satisfying way? And so that really will be our preoccupation for the rest of the lectures. But I think that's good enough for today. Thanks very much. Any questions?